We ready? Some of you might notice there's some apparatus in the room today, so I'm giving this a try. We're going to start trying to record these lectures, and I'm going to be making the lectures that I record available on my YouTube channel. So this is, hopefully that you find that useful, and it might take me a little while to get the recipe just right on how to do this, and so I appreciate y'all's patience in that process, but hopefully you have a good time with it along with me. All right, so what we're going to do now, I think I talked last time about that the first part of this course has been all about the sort of the fundamentals behind stress transformations and some of the basics that we're going to be using for the next part of this course, which is the part where we talk about coming up with theories that hopefully describe when things will fail. And that's where we're going to go today. Before I get into that, I'm actually going to take one little side path here to talk about something that is a kind of a big deal with respect to designing of things for static loading. There is a very common assumption that gets made when you're getting ready to design something for static loading, and it is that we ignore stress concentrations. So you guys might remember back in Engineering 220 that we had a method where we could figure out what the maximum stresses were in a part that may have discontinuities of some kind. You could figure out what those maximum stresses were using charts and a lot of that kind of stuff. That is very useful, particularly for materials that are more brittle in nature. And we will find out in the next part of the course it's also useful when we're starting to talk about fatigue. When we are looking at static loading of ductile materials, it is a lot less important for us to deal with those stress concentration factors. And so I'm going to try to justify that for you right now here just a little bit. So let's do that with respect to a tensile specimen. We'll zoom in really closely. A dog bone shaped tensile specimen might have a shape something like this. And we'll zoom in really tightly on a portion of this dog bone shaped specimen that might be loaded in an axial way like this. Where it has this geometric discontinuity, if you identify a little patch of material in here, maybe somewhere right around here or maybe slid down a little bit, that patch of material is going to experience a stress concentration due to the fact that there is a change in geometry that happens here. That whole idea of the stress concentration kind of comes about because you go from a higher level of stress where you have lower amount of area up to lower amount of stress where you have higher amount of area, and in that transition the material is not actually allowed to open up holes or anything like that, so the continuity requirements that you have for the material itself gives rise to these inequities in the amount of stress that you have in the different spots. And so that's you expect for that little patch that I drew right there to experience stresses that are higher even than you would have predicted for the smallest cross-sectional area of this part. But here's why we may not care. So what I want to show you here is our stress-strain diagram. For ductile materials, where we have stress versus strain, it is a normal thing for us to look at this diagram and have an elastic portion where it has a linear shape to it, and then it has another portion where it tends to deform quite a bit more, and then maybe it'll break at some location. So this is every material may not look exactly like this, but this is a generalized idea of what a ductile metal might do whenever you begin to stretch it to the point of failure in terms of the stress and strain. All right. Well, that curve that happens up there on the top, there are methods that we can deal with that curve, but one way that this is sometimes dealt with whenever you're doing things like finite element method or that kind of thing, one of the ways to deal with that is a model that's called an elastic, perfectly plastic model. Okay, so that green line that I'm showing right there, this is elastic, perfectly plastic. Okay, and basically how we could interpret that in terms of, conceptually what it's doing, the material is, it behaves in an elastic way, meaning that as you load it on the left portion of that curve, any load that you put, as long as you don't go over that break point, any load that you put on there, if you take it back off, it will return to its original size, right? With the elastic perfectly plastic model, basically it says once you reach that yield point, then you can continue to deform the material at the exact same amount of load / stress for a certain amount of time. And if you were to do that, then when you unloaded it, it would unload along a line that would be parallel with the elastic portion. All right. So if you understand how the material might behave and use this sort of simplified model of how the material might behave, it helps us to understand what might go on in a piece of material there that has a stress concentration, where the stresses are concentrated right there. What we expect might happen there is that that piece of material will yield first. Would you agree with that? The piece of material that has the stress concentrated on it, it will begin to yield first. So let's actually sort of play forward in our mind. If we are loading this tensile specimen, and right here at this geometric discontinuity we have a stress concentration, and so it begins to yield at that little patch of material first because that's where the stress concentration is the highest. What happens after that? Think about this, you can think about this in terms of stress fields in this material. Yeah, so this little piece of material right here might increase, if let's say the stresses are this direction, it might be able to increase in length just a little bit because it's gone up into this perfectly plastic region of this model, but it continues to hold load at the same level as it did before it started to deform plastically, right? Well, what does that do in terms of the distribution of stress throughout the rest of the cross section? Yeah. Yeah, it'll actually take that high stress that you have concentrated at that one location and move it more to the center. As a matter of fact, if you continue to load this thing through a certain amount of plastic deformation, then the stress distribution will actually approach being uniform across the cross section. So that's what we expect to happen with these things. Because of that, this is the reason why we can frequently ignore the stress concentrations that happen in a material as long as it is a ductile material. What would this curve look like for our stress strain if we have a brittle material?
There wouldn't be as much elongation, it would rupture really quickly.
Yeah, so it has the elastic portion if it's a brittle material, but then what? It breaks, right? And where it breaks, it doesn't continue to carry load, right? So if this is made out of a brittle material, this tensile specimen idea that I have over here, then as soon as that little piece of material that I've identified right there reaches its point of failure, then it stops carrying any load and reduces the amount of area that's still left to carry load. And so how a member fails is significantly different if it's brittle than if it is ductile, right? And whether or not we need to account for these stress concentrations, it becomes much, much more important. It actually becomes absolutely critical to deal with your stress concentrations if you are dealing with brittle materials. But if you're dealing with ductile materials, you can often ignore them, because what happens is by yielding a little bit, it tends to equalize the stress across the cross section. That kind of interesting? So anyway, I thought I'd mention this. Most of what our failure criteria that we're going to look at, most of them are more or less tailored for ductile materials because that's what we work a lot with in engineering. We like those materials. They give us a little bit of more warning before they break. They are, a little bit more robust against these stress concentrations. We tend to like ductile materials instead of brittle if we can get them. But one of the things that happens, though, is that if you process a steel, for instance, a lot and get it really, really strong, one of the things that happens is it tends to become more brittle as it becomes more strong. So we can't always avoid using brittle materials. So anyway, this was a little sidebar that I wanted to start with and talk about why we sometimes ignore the idea of stress concentrations for ductile materials. All right. So the actual stress, or the failure criteria that we're going to look at today is called the maximum shear stress failure criteria. And I want to give you a little bit of justification as to why this criteria exists and maybe how people sort of came to know that it might exist. I'm going to do that in the context of a couple of pictures here of some tensile specimens. These tensile specimens, the one here on the right was loaded, you know, in an axial way like this. The one here on the left was loaded in an axial way, but, you know, in this other direction. And it's really hard to get a good picture of what I'm trying to show you here. These are a couple of the better ones that I could find was when I looked around online for pictures of this idea. But what we have on these specimens are a bunch of lines that began to appear as the specimens started to go into their plastic state. All right? And one of the things that you see fairly clearly on this one is that there are these lines that are sort of generally at 45-degree angles. Do you see this? And on this other one over here, this one, again, you may not be able to see that very well from where you're sitting, but if you look really closely at this piece of material, you get to kind of see that there's a bunch of lines that are sort of all at 45-degree angles relative to the direction of load. Okay? So this is one of the things that when a piece of material begins to fail, a lot of times these lines start to show up, and these lines are sometimes known as slip planes. Right? They basically start to slip, and they show these lines on the surface. This gave rise to people sort of beginning to, you know, hypothesize that there might be some sort of a failure process that happened on these planes. And so what's interesting about this is if you imagine there being an element of material that is loaded purely axially, and you imagine, so let's say that's just a stress that's loaded purely axially, what would the stress look like on a plane that was at 45 degrees? To have a good amount of shear on that plane. All right? If you think about this, let me actually draw the Mohr circles that would be associated with a state of stress like this. All right? You would have your shearing stress up here. You have your normal stress right here. For a tensile specimen, it has a uniaxial state of stress. Where would I plot my principal stresses on that? What would you think? Okay, whatever that stress value was would be here in one direction. In the other two principal directions, we'd be at 0. So what would our Mohr circle diagram look like? Just one circle. Okay. And if I go to this plane that's 45 degrees, what happens there? Or where is that on this circle? Okay. Yeah, that's at these points right here. That is where the maximum shearing stress occurs. Okay. Excuse me. And so I know this doesn't do it rigorously, but it gives a little bit of justification or some clues as to how this failure criteria came to be. And so I'm just going to state what this failure criteria says. It basically says that when the stress on a part in service actually, when I need to add in here, when the maximum shearing stress on a part in service reaches the amount of shearing stress in a tensile specimen that causes it to fail. We predict that the part will fail. All right, so there's kind of a lot there, I know, but what we're going to try to do here is show some examples and and kind of get us to see several different ways that that this could happen. All right, so for any given state of stress, we can express it in terms of a Mohr three-circle diagram. Would you agree? The Mohr three-circle diagram shows your three values of principal stress. You can kind of show that, all the different possibilities that we could have, we can express in terms of some Mohr three-circle diagrams. Okay? And, what we'll do, though, is we'll actually focus on three different possibilities of plane stress, because it's the most common type of stress that occurs at the critical locations on parts, because the critical locations on parts usually happen on a free surface, and so the part will fail at a location where there's a state of plane stress. And so we're going to look at the three different possibilities that we have for that. One possibility is this. Okay, one possibility is that on our Mohr diagrams here, we could have a state of plane stress such that our two principal stresses are over here in the right half. Okay, so these are my two in-plane stresses, and for a lot of our work that we're going to do in here, we're actually going to use notation of sigma A and sigma B. So I'll use that notation here. I do this instead of using sigma 1 and sigma 2 because sigma 1, sigma 2, and sigma 3, the standard way of using those is to order them in descending order, right? Where you put sigma 1 as being the most positive one, sigma 3 being the most negative one, right? I want to break loose of that a little bit, instead use different terminology, but the sigma A and sigma B are still principal stresses. They're just the in-plane principal stresses, okay? If this is a state of plane stress, where is my third principal stress? 0. So my Mohr three-circle diagram looks like what? Something like this, where that's my third principal stress over there. Okay. Well, what is my what is my maximum shearing stress for a part that's loaded in this way? It'd be here and here. It'd be the radius of this circle. What's the radius of this circle? Sigma over 2, right? So sigma A over 2. Okay, this is our maximum shearing stress. And if this part, let's say this is the state of stress that I have in a particular part, if this part is on the verge of failure at this stress state, what would that be in terms of this failure criteria that I have defined? This thing would be equal to what? Okay. The next part of it is we have to think about how much shearing stress exists in a tensile specimen when it fails. Okay. Let me do that up here. Let's say that this state of stress that I identified right here, this is a tensile specimen loaded right to the point where it's about to fail, right? It's right up at that point of yielding, okay? This sigma that I put over here would be what? This is a piece of information we can look up in tables. It would be sigma y, or in this book's context, we usually call that S sub y. All right. This book uses capital S to talk about strength properties. So strength, yielding strength, is capital S sub y. Okay. And so what would the shearing stress be in the tensile specimen at this point of failure? S sub y over 2, right? So because the radius here is half of the diameter, and the diameter is S sub y, right? So what this basically says is that this is going to be equal to S sub y over 2. Okay? And, you know, we don't necessarily care. I just put this tau max in there to indicate that that was the maximum stress that occurred in this case. So what we'll say here then is that when your maximum in-plane shearing stress equals your yielding strength, this is, you know, we would begin to predict failure. And actually, I'm going to state it in terms of an inequality. What inequality would we predict failure, would you think? If sigma A is greater than or equal to, right? If sigma A becomes greater than or equal to your yielding strength, then you predict failure. That's pretty simple. Okay? Let's do one that's a little bit less simple. What happens if you have a part that's in service? And let me do it this way. You have a part that's in service, and now your in-plane principal stresses are, say, sigma A and sigma B. And so you draw your Mohr circle like that. Where's your third principal stress? Still at 0. Okay, so your 3-circle diagram looks like this. Something like that. Okay. What's my maximum shear stress? Okay. So it's the difference between the two positions along the number line divided by 2, right? Sigma A minus sigma B divided by 2. This is equal to my maximum shearing stress. All right. As far as the tensile specimen, that criteria didn't change, right? The tensile specimen criteria is still whenever you reach, or the shearing stress that you have when your tensile specimen is about to break is going to be half of your yielding strength. All right? So we say this is still going to be S sub y over 2. Okay, and this is kind of interesting because now sigma A is going to be equal to what? Sigma B plus S sub y. That actually kind of defines a linear relationship, you know, and we'll get into that here in just a second. But that's our, you know, a second possibility here. What's the third possibility? Okay, the third possibility is your two in-plane principal stresses might both be to the left of 0, might both be compressive, right? So you could have sigma A here and you could have sigma B here. And that would give you this Mohr circle, which means that your overall principal stress, overall shearing stress would be defined with this circle that went back to 0. Okay, and on the same type of logic that we had a minute ago for you know, sigma A, over here we would say that the shearing stress that we have for this particular thing would actually be, and I'm going to throw a minus in there to kind of make it make the numbers work. Minus sigma b over 2 would be equal to S sub y over 2, which, you know, just basically means that sigma b would be equal to negative sigma y, or S sub y, excuse me. All right. So these are our three possibilities. And what I'm going to show you now is a plane where we plot these possibilities of failure. And I'll tell you what, I'll go ahead and make these other ones expressed in terms of inequality as well. Okay. What we can do is we can use those equations and plot where we expect failure on a set of axes that basically give you the two in-plane principal stresses. Okay. And so we'll basically plot it where we put our sigma A over here and sigma B up here. Okay. So if sigma A and sigma B are both positive, let's say sigma A is greater than sigma B. Okay. If sigma A is greater than sigma B, then where do we predict failure if we were to plot it on this set of axes? Okay. We basically draw this vertical line, right? Because as soon as that stress gets larger, you know, it really only takes one stress. As soon as one stress gets larger than S sub y, then we predict failure. Okay. What happens if sigma B is greater than sigma A? Okay. There's a limit, right? At some point, it caps off up here. Okay, so what if sigma A and sigma B are both positive, what we've done here is we've basically said that if we load with our two in-plane principal stresses somewhere in this envelope, we won't fail, right? In here, we predict that we are safe. Out here, we predict failure. Okay, so this is one side that's not too hard to do. What about if both of them are negative? Okay, we'd go down here and we'd say, okay, let's look at, this would be negative SY. And then I could do the same thing over here. And it's kind of like it does in the first quadrant. Okay, and it's safe in here. And out here it fails. All right. Now what if one's positive and one's negative? Okay, let's actually think about this is the formula here that pertains to this. Okay. Yeah, essentially it allows us to connect a straight line like this. You can connect that straight line along those two directions. So what we have here is that inside of this envelope, we do not predict that the part will fail. Outside of this envelope, we do predict that the part will fail. All right. This is a graphical representation of the maximum shear stress failure criteria. All right. It's a very simple failure criteria. You know, it's because the math is simple. It is used commonly. We're going to learn about another one next time that's called the distortion energy criteria. And so I'll talk a little bit more about this one with respect to that one in a little while. One thing I want to do, though, right now is I do want to look at a special type of stress, a special state of stress. What does the state of pure shear look like on Mohr's circle? Okay. On Mohr's circle, where we have tau and sigma, if you have a state of pure shear, what does that look like? Okay. Yeah, you'd have no normal stresses. So the two vertical lines that you would plot for Mohr's circle would be right here on the, right at the 0 point. And then what? You'd plot whatever state of shear that you had, and it would look like a circle like this, right? Okay. Where would the principal stresses be? So let's just say that this is, I'll just say that that is a state of stress tau. Well, you'd have plus and minus tau, right? Those would be the principal stresses. Okay. So if you have that, one of the principal stresses is equal to the negative of the other principal stress, what line does that draw on this sigma A, sigma B set of axes? Okay, it's similar to basically saying, what if y is equal to negative x? Right? So what line would we see on there? Okay, this is pure shear.
Why does that go through the origin like that, at that angle? How can we tell?
We can tell because where we have a state of pure shear, our principal stresses, one is going to be the negative of the other. They'll have the same magnitude, but opposite sign. And this line that I just drew is the set of all points for which you have the same magnitude and opposite sign. Does that make sense? In other words, I could pick a point along this line. I could pick a point right here. Right? And let's say that I had, my sigma A in plane principal stress was 10 KSI. What is my other in plane principal stress? All right, it's 10 KSI this way. It's negative 10 KSI this way. Right? And so, what I'm showing you over here with Mohr's circle is that once you say you've got a state of pure shear, the other way of saying that is that your two principal stresses are basically negatives of each other.
Oh, okay.
Right? One's tension, the other's compression.
Okay.
All right, so that is the idea of the maximum shear stress theory. Let's do a quick example. Okay. Let's look at the example where we have a state of stress where we have sigma x equal negative 17 KSI. Sigma y is equal to 20 KSI. And tau xy is equal to 11 KSI. Okay, and this is the state of stress We'll say it's a state of stress at critical location. What do I mean by that? The critical location of a part. What's the critical location? Yeah, it's the location in the part where we expect failure first. Okay? So this is the state of stress we have at the critical location of a part, and that part is composed of 1020 HR stands for hot rolled. We'll get used to that terminology that a lot of our materials are going to be either hot rolled or cold drawn. So HR is hot rolled, CD is cold drawn. Steel, I should say that. Okay, and what we want to do is we want to find our factor of safety using the MSS criteria. And furthermore, I want to, so that's one thing I want to do, and then next I want to plot a load line, and I'll show you what that means in this context. We'll plot a load line on the failure locus plot for this material. Okay, so what do you think our first step is going to be here? We probably need the principal stresses, right? So how do we get our principal stresses? Okay, I would say our two principal stresses that we are going to have, we can find those using our equation that we use for Mohr's circle, right? So we basically take the average of our two normal stresses, so 20 KSI plus a minus 17 KSI over 2 plus and minus square root of what? 20 KSI minus a minus 17 KSI over 2. All of that squared. Plus our shearing value, right? 11 KSI. Squared. Okay. And to save us the time, what I came up with for this is that sigma A is 23 KSI. And sigma B is negative 20 KSI. All right. How do I plot my failure locus? Okay. Well, one of the things I need to know is for this hot rolled material, it's 1020 hot rolled. All right. I need to know what's the strength for that material. So what we do is we find what the strength is for that material in one of the tables that we have in the back of the book. One of the tables we use an awful lot is A20. it has several different types of steel and the strength properties for all those types of steel. Okay. 1020 hot rolled. It says that our tensile strength, which is another, in this particular table, that's what they refer to as the ultimate strength. They just call it the tensile strength in there. Those are synonymous for the purposes of this table. And then it says yielding strength is 30 KSI, and that's what we're concerned with, is the yielding strength. So S sub y is equal to 30 KSI. Okay, so how do I plot this failure locus? Well, I take that S sub y and I go ahead and I draw my limits, right? Basically plus and minus S sub y in every direction. Correct? Okay, so let me just, I don't know, maybe we'll call each square 5, I guess, 5 KSI. 5, 10, 15, 20, 25, 30. Okay, this is our failure locus. And again, if you're inside of there, you're doing okay. If you're outside of there, you're not doing so good. All right, how do we plot our particular state of stress? Well, we look at this and say we've got 23 KSI along our A direction. So 5, 10, 15, 20, not quite to 25, so we're somewhere along here in this direction. And then what about our other direction? 20, so we have 5, 10, 15, 20. To plot the load line, a load line is plotted basically by drawing a line from the origin to this set of coordinates for this load. All right, so this blue line right here, this is the load line. Here's the significance of the load line, so that I kind of mentioned why this is a thing. For a lot of parts, how much they are loaded in all the different directions just winds up being proportional to how much applied load there is. And a lot of times that applied load is maybe sometimes just one load. And so you put one load on there, and then the stresses in all the different directions increase proportionally to each other with that amount of load that you apply. Do you agree with that? So that can happen a lot of times, where you have all of your different components of stress increase proportionally to each other as you increase the amount of applied load. What that does in terms of this load line is, if you were to increase or decrease the load, increasing the load would push you further out on this load line. Decreasing the load would pull you in along this load line, but you would always be on that line if all of your different elements of stress stayed proportional to one another. Does that make sense? So where this doesn't work so well is if you have multiple different types of loads. So like think about a case where you might have a pressure vessel that also had other loads on it, right? Increase the amount of pressure in the pressure vessel, that will not necessarily proportionally increase all the different components of load just by increasing pressure, because you have all these other forces on there as well. As if it's a pressure vessel and the only load that you have is the internal pressure, and increasing and decreasing that pressure will likely just move you along this load line, or whatever load line that you would have, right? that make sense? So a load line is basically a way to understand if you increase and decrease the amount of load that you put on a part, you can move from being safe to being unsafe as you move outside of the this failure locus. Okay? So does it look like we are safe? Okay? Well, how would we know that in terms of numbers? Well, we have to go up here and find the case that matters to us. Is sigma A greater than sigma B plus S sub Y? Actually, I prefer looking all the way up at the original statement of it. Is sigma A minus sigma B, is it going to be greater than S sub Y? Okay, and one of the things that we have to do is that we have to make sure that we put in the numbers with the signs that they have. All right, so I'll go down here and say, is sigma A, which is 23 KSI, minus a minus 20 KSI, okay, is it greater than or less than S sub Y? Okay, it's going to be greater than 30 KSI. That means that we plan that this thing is probably going to fail. All right, so what do we do to deal with the actual factor of safety? Well, let's actually flip back to this section in the book, because I want to point out that the other thing that they prepare for you there in these sections is expressions of these failure criteria that also include factors of safety. I'm finding it right now. I couldn't remember it off the top of my head. It's on page 234. Okay. On page 234, equation 5.5 shows us the expression of that, that I had. If you move up a little ways, it shows it to you with this variable of n. All right. This book generally uses n as a factor of safety or as a design factor. That's usually the letter that they use to talk about factors of safety. And so you see there, equation 5.3 says if we have the difference between these two values, it's going to be equal to the yielding strength over the factor of safety. Okay, and if you solve for n here, n becomes 0.697. Stuff's actually not that hard. That's it. So we've now dealt with maximum shear stress theory as one of the possible failure criteria that we have here, or failure criterion. Okay. This would be a great time to also mention one of the things that you probably learned when you were in Engineering 220 is that you learned if you don't have a value for the shearing strength of a material, you are allowed to do something to give you an estimate. What did you do? You looked at the yielding strength and you took half of it. Okay? Now, having looked at all this stuff, what's the justification for that? Tell you what, I'm going to scroll up to where we had, can't remember where it was. There it is. All right. This is the Mohr circle for our tensile specimen, right, at the location or at the amount of load right where it begins to yield. When that begins to happen, it develops a shearing stress in here that is going to be half of that shearing strength, right? And so what you basically do is you say, okay, well, that's how much shear it takes to break this part. What this failure criteria says is that that's no different than if you had a state of pure shear that was centered here, right? If it has a positive and negative of essentially S sub y over 2 and negative S sub y over 2, this failure criteria says those two things are at exactly the same level of peril for them to possibly fail. Does that make sense? So this is where we came up with this idea that we can take S sub y over 2 as a reasonable estimation of what the yielding strength is if you don't have it given in a table, for instance.
Yielding strength, not the same thing as SY
SY is yielding strength. So, but if you don't have a yielding strength in a shearing orientation given in a set of material properties, yeah, I should have said that a little more clearly. If you don't have it in a shearing orientation, then you can find out what it is. If you have it in the normal orientation, you can figure out what it is using that. Next class period is going to be even more fun because the next class period we get to look at the maximum or the strain energy density. All right, we look at the energy criteria, distortion energy criteria. All right, and we'll actually come up with a slightly different estimation of how much strength we can expect out of a piece of material using that failure criteria.